Okay, welcome to class, guys. So just a reminder before we start, I did send out the link to sign up for the small lab project. Again, it's not something to really stress out about. There will be more details to follow, but you'll need to set up a time with you and a group to go in and spend some time in the innovations lab with Dr. Pershing and work through this assignment. If you didn't notice, I created a special assignment where you get some points just for signing up in a group. So make sure that you're in a group of at least 2, up to 3, and I'll just leave that up to you. On the due date, or after it's due, I'm just going to go in, look at the sign-up sheet, and see who has successfully signed up. So I need to see everyone's name. You can't have someone else sign up for 2 or 3 slots, and then just assume that I'll figure out who's in. They need to list your name in the comments or something, so your name has to be on there. Otherwise, I have no way of knowing who signed up. Okay, so today we are going to be starting internal flow. So we're still talking about convection. Now we're moving on to chapter 8. This chapter has some pretty good, pretty meaningful theory to it and derivations to it that are going to be important. So I like this chapter a lot better than chapter 7. Personally. Okay. So what does internal flow mean? If you recall, in chapter 7 we talked about external flow, which is flow around a cylinder, or around a sphere, or over a flat plate. So the flow was unbounded. So in internal flow, the flow is basically bounded. It's going through some well-defined channel, so like a pipe or a duct or something. So one of the implications of that is that while we still care about this concept of a boundary layer forming, both the velocity and the thermal boundary layer, unlike in the flow over the flat plate where that boundary layer just kept growing and growing and growing, now the boundary layers get to a point where if you have a boundary layer forming on the top of a pipe, let's think of a square pipe or some sort of flat channel. If you have a boundary layer growing from the top and the bottom, eventually those 2 boundary layers are going to converge. And so they run into each other, so they stop growing and your flow becomes fully developed. And that means your velocity profile will get to a point where it no longer changes with distance down the pipe. It just gets to a point of being fully developed. Similarly, the thermal boundary layer, or the thermal profile is a little bit different. So fully developed is going to be defined a little bit differently, and we'll explain that as we go. Okay, so as I mentioned, there's still this idea of a boundary layer. If you recall, when I talked about external flow, I used the example of flow going over a table. So when the flow interacts with what's called the leading edge of the table, you start to get friction happening, and your heat transfer may just happen if there's a different temperature between your surface and the bulk fluid. So that still happens when you have flow through a pipe, except really it only happens at the entrance where that boundary layer is still forming and growing. So that's going to be what we call an entrance condition. So the entrance condition is going to be before those 2 boundary layers converge. So if you see these boundary layers start to grow, eventually they sort of run into each other, and then you get this constant velocity profile. So from this point on out, if you took little snapshots of the velocity profile, you'd see that they were all identical going forward. So what that means in terms of heat transfer, it means that your system might behave a little bit differently in this entry region as compared to the fully developed region. So the good news is, in the fully developed region, things sort of level out and become constant, and it's much easier to deal with them mathematically. So the velocity boundary layer develops on the surface of a tube and thickens with increasing x. You get this inviscid region so the uniform velocity shrinks as the boundary layer grows. So here's the inviscid region where we just assume that the velocity is all constant and uniform. That's called plug flow, which you'll learn about in kinetics, I believe. So that inviscid region shrinks, and you get to this point where the velocity is really never constant with respect to r, but it does become constant with respect to x. Okay, so the way that you solve for the velocity profile would be by doing a momentum balance. We don't really use that much in class other than just being aware that you have this changing velocity profile with respect to the radius of your pipe. So I'm not going to go into depth into that derivation unless you want me to. I'd be happy to do that in a later lecture, but knowing you guys, I kind of doubt you're going to want me to do that. So you do a momentum balance and you look at the shear stresses and how those different layers of fluid are interacting with each other. You'd solve that and you would end up with an equation that gave you velocity as a function of r. So here's r. So the velocity here is going to be highest. So the x velocity is going to be highest at r equals 0, and then it's going to be lowest at r equals the inner radius of our pipe. We will deal with, so frequently, we're going to be aware that there's an actual velocity profile, that the fluid's going to be flowing the fastest at the center of the pipe, and it may be, if we have a no slip condition, it'll be 0 on the edges of the pipe. So we'll be aware of that general concept, but we'll typically think of things in terms of the mean velocity. So the mean velocity, and really it's just what you would think of if you've had your 2800 class, right, and you remember the formula, m dot equals rho times velocity times cross-sectional area. So really what you're getting out of that is you'd be dealing with the mean velocity in that case, and you'd just be treating it, instead of treating our velocity with some sort of shape, we'd just say, okay, what's the actual mean? And we'd treat the whole fluid as if it were all at that mean. So you can get the mean velocity by integrating, if you knew the actual velocity profile. So if you had u as a function of r and x, you would just integrate that over the entire cross-sectional area, divide that by rho times the cross-sectional area, and you get the mean velocity. So we won't really need to deal with that much other than just remembering there is a velocity profile, but we'll typically just assume that the velocity is all uniform by calculating or by using its mean velocity. So we talked about entry lengths, just like with fluid flow over a flat plate, where when you encounter the leading edge of the flat plate, there's going to be a different velocity boundary layer and a different thermal boundary layer. And if you recall, we had formulas to calculate what the velocity and thermal boundary layer thicknesses were. So I just want you to remember that we treated velocity boundary layer and thermal boundary layer differently. So similarly here, you might have different hydrodynamic entry lengths than thermal entry lengths, which means your velocity profile may take a certain distance to develop, and that may be different than the distance that it takes your thermal boundary layer to develop. So entry lengths are going to depend on whether the flow is laminar or turbulent, which is going to depend on the Reynolds number. So a Reynolds number for flow through a pipe or through a channel is going to be defined as rho times our velocity times d divided by our fluid viscosity. So that d has a subscript on it, h, and that refers to the hydraulic diameter. So the hydraulic diameter in the case of a circular pipe is just the diameter. So nothing to worry about there. If your pipe is non-circular, like if it's a square or rectangular channel, then you would calculate the hydraulic diameter as the hydraulic diameter is equal to 4 times the cross-sectional area divided by p. Any guesses as to what p is? The perimeter, yeah. So let's just as a sanity check, let's just calculate the hydraulic diameter real quick for a circular pipe. Okay, so what is the cross-sectional area for a circular pipe? I know some of you know it. I know like a third of you know it from grading your exams. Pi r squared, great. Pretty easy. That's like 8th grade math. Okay, so we can also express that. Let's express it in terms of diameter. So we're going to have 4 times a sub c. So if we want to express it in terms of diameter, then it's pi fourths times the diameter squared. Okay, and what's the perimeter of a circular pipe? yeah, what did you say?
I said 2 pi r.
Yeah, 2 pi r, or pi times d. Okay, so the 4's cancel out, pi cancels out, and that ends up just being equal to d. So nothing to worry about. We just use diameter to calculate Reynolds number for a circular pipe. But if it's not circular, then you'd have to go through this calculation of calculating the hydraulic diameter. So for a circular tube, our Reynolds number is just how we've always, the Reynolds number that we're familiar with. And you can put that in terms of mass flow rate by doing some algebraic manipulations. Okay, so I've launched an interactive problem. So I want you to calculate quickly what is the hydraulic diameter of a rectangular tube that's 5 centimeters wide and 3 centimeters tall in centimeters. Just to help you, I should have hidden the answers. Okay. So it is 3.75 centimeters. Good job. Okay. So the hydraulic diameter, just the diameter, is going to tell us a little bit about what the entry length is. So basically, this entry length is when those boundary layers are still developing, what happens at the very beginning of our pipe is going to be different than what happens after the flow becomes fully developed later on in the pipe. So that's sort of the motivation for talking about entry lengths, is we'll have to treat that entry length a little bit differently from a heat transfer point of view than we will the rest of the pipe. So I'm sticking with the book standards. So according to this particular textbook, the onset of turbulence occurs at a critical Reynolds number of 2300. So what's the number you're used to from fluids? It's what? 2400. Okay, so this is about in that same range. This is not exactly a perfect science. So you'd start to get transition to turbulence when you have a Reynolds numbers of 2300 or greater. And then you would, if it's above 10,000, then you can very safely assume that your flow is fully turbulent. So we get these little rules of thumb that tell us how long is our entry length, or how long does it take those boundary layers to develop, what's the section of pipe that we need to treat differently than the rest of the pipe. So for laminar flow, so the hydrodynamic entry length, when it says hydrodynamic, that's referring to the things changing with respect to velocity. So for laminar flow, our hydrodynamic entry length is going to be defined as, so it's put in this ratio. So our hydrodynamic entry length is x sub FD. So that stands for when the flow becomes fully developed hydrodynamically is equal to 0.05 times our Reynolds number. So you would calculate the Reynolds number. So unlike flow over a flat plate, where the Reynolds number keeps on getting bigger and bigger because it's a function of x, here our Reynolds number, as long as our pipe or channel is the same size down its whole length, our Reynolds number is going to be the same down the whole length. So our Reynolds number is just going to be a constant that's going to be a function of the diameter, or the hydraulic diameter of our pipe. So we would just calculate our Reynolds number, and then we would multiply, so we would get x FD, comma H is equal to 0.05 times our Reynolds number multiplied by the diameter of our pipe. So it depends on the diameter of your pipe. So for turbulent flow, similarly, that's going to occur. It's not a function of Reynolds number, interestingly. That's going to occur somewhere between 10 and 60 pipe diameters. So our flow would become fully developed at a minimum of 10 pipe diameters in terms of length down the pipe. So our thermal entry length, we also have a similar correlation. So for laminar flow, it's very similar, except we use this combined dimensionless number of our Reynolds number times our Prandtl number. But then the turbulent flow correlation looks the same. So if the flow is turbulent, we would expect our hydrodynamic entry length and our thermal entry length to be basically the same. Okay, so let's actually calculate for the rectangular pipe that has a hydraulic diameter of 3.75 centimeters. What is the minimum estimated hydrodynamic entry length? So it's turbulent flow. Our hydraulic diameter was 3.75 centimeters. So we would go back and we would use, so I'm asking for the minimum hydrodynamic entry length, so we'd use this 10. So we'd assume that after 10 pipe diameters, our flow would be fully developed hydrodynamically. So how long does it take for our flow to become fully developed? And let's go. Oh, I don't think I actually gave you guys the option to answer this question yet. Let's just wait. Looks like we're kind of sparse today, probably because fall break is coming up. I'll just wait until 10 people answer it. All right, great. So our hydrodynamic entry length would be 37.5 centimeters. So what that means is for the first 37.5 centimeters, we're still going to have those boundary layers developing. And then after that, our flow is going to be fully developed, and we can just treat things, we can treat our velocity profile as being fully developed. It'll also have some heat transfer implications that we'll discuss later. Okay, so let's say that we have a pipe that is 200 meters long, and we're asked to do heat transfer analysis on that pipe. So our pipe is 200 meters long. How much of an impact is that hydrodynamic / thermal entry length going to have on our pipe? Say that again?
For the same pipe?
Yeah, same pipe.
Not very much.
Yeah, so if our pipe is 200 meters long, and this is the first 37.5 centimeters of our pipe, it's really not going to matter. So in that particular case, we could say that our entry length is sort of negligible, and we could just treat the whole pipe as being fully developed, which will make our calculations a lot easier. And frequently, the problems will kind of assume that flow is fully developed all the way down the length of our pipe. Okay, so we can also get thermal effects. So similarly, when that flow enters our pipe, if we're assuming that it enters all at uniform temperature with respect to R, if we have a heated pipe, that heat is first going to penetrate the outermost fluid, and then eventually that thermal boundary layer is going to form. And when those two thermal boundary layers merge, the flow is said to be fully developed here. Except there's a key difference here. So in this particular case, if we had uniform surface temperature of our pipe, for example, what we would actually witness is that this gets more and more elongated the further down you go, because the pipe surface temperature stays the same, but your inner fluid, your inner fluid still has this more extreme temperature difference. So we treat this a little bit differently. Okay, so similarly to the mean velocity, there will also be a mean temperature, and our textbook treats this mean temperature with this, they denote it as this T sub with a subscript M. I don't personally love that, but I'll try to stay as consistent with that as I can. So it's important to remember that there will be temperature gradients radially in your pipe. However, we'll typically treat our heat transfer correlations in terms of the mean temperature. So we'll assume that our temperature is going to change with respect to X, our temperature is going to change with respect to X. That fluid, if it's a heating application and the pipe surface temperature is constant, our fluid's going to get hotter and hotter the further down it goes. But we'll still have, in reality, we'd still have temperature changing with R, but we could calculate the mean with respect to R so that we're only dealing with temperature change with respect to X. So that's done similarly by taking an integration. So we'd be integrating from 0, so where the radius is 0, the very center of our pipe, and we would calculate the velocity times our temperature. So notice the temperature here is a function of both X and R. So we integrate that over the whole radius, and we end up with our mean temperature. So our mean temperature is going to be a function of X only, because we're going to assume that basically by taking the mean, we're going to neglect any temperature change with respect to R. So Newton's law of cooling, this local heat flux form, will still very much apply. So the flux is going to be proportional to our local heat transfer coefficient multiplied by our surface temperature. This is assuming a constant surface temperature, or even not, and our mean temperature. So I've got a question coming up asking us more about that. So because our thermal profile is changing, because our fluid, unlike in the velocity case, so our velocity profile develops, and it's basically that same velocity profile. However, the thermal profile is different because our fluid is being heated up as we go. So our thermal profile changes, so defining fully developed flow is a little different. And basically, what this means, the definition of fully developed flow is saying when the partial derivative with respect to X of this normalized temperature profile, so our surface temperature is a function of X minus our fluid temperature is a function of R and X, divided by our surface temperature divided by our mean temperature. So it's important to note that mean temperature is still a function of X. So when things get fully developed, this condition will apply. And so what that means is we may treat our local heat transfer coefficient, it may be very different at the beginning of our pipe. So this would be the entry length. So from a heat transfer perspective, as those velocity and thermal boundary layers are developing, our local heat transfer coefficient at the beginning of the pipe is going to be changing. But once our flow becomes fully developed thermally, our heat transfer coefficient is going to level off and be a constant. And that is going to be a really nice thing for us to deal with mathematically, to treat our local heat transfer coefficient as being constant or averaged out from that point on. Okay, so this mean temperature, so I want to carefully explain again, the mean temperature means we're averaging our temperature with respect to R, but it's still going to be changing with respect to X. So we're basically treating our fluid as being uniform in temperature with respect to R, but it would be changing as the fluid is heated or cooled going down the pipe. So to determine our mean temperature, we're going to start by doing a derivation. And so this is going to be a similar approach to when we've been using the heat equation or the thin fin equation. We're going to start by taking a differential energy balance. So this energy balance, and this is going to be an important concept to internalize. So if this is our pipe with X, we have our fluid coming in at a certain mean inlet temperature. Our approach here would be we want to calculate what's our mean temperature as a function of X. So I want to open this up to you, actually. What should be our approach here to calculating our mean temperature as a function of X? You're not raising your hand, you're just thinking, okay. So we could do an energy balance here. So we would take our pipe and we could break it up into these discrete volumes. So let's say we're going to look at this particular volume. So we're going to have flow coming in and flow going out. We're also going to have energy coming in with a constant flux, a constant surface flux of Q sub S. Okay, so how do we do an energy balance? Okay, accumulation. And I didn't specify this, but let's do this at steady state. So our accumulation will be 0. Then we're going to have in and out. And I also didn't specify this, but let's assume that we have no generation, just a fluid flowing through a pipe. Okay, so now this is a little bit different than the rate terms that we've used. So when we dealt with conduction, our rate terms, everything was stationary and just sitting there. So our rate terms came from Fourier's law or Newton's law of cooling. So in this case, we're going to have energy passing through our control volume by flow. That's called advection. So advection is basically when energy is carried by a fluid flowing. So how is energy getting into our section of pipe here? I'm hearing someone saying it. Okay, great. M dot Cp times T evaluated at X. So fluid coming into this node would be coming from the node immediately before it. So whatever temperature is here, that's going to be the same temperature of the fluid entering our system. Okay, great. And we're cheating a little bit here. We're assuming a constant heat capacity here. So really, enthalpy is relative to a reference temperature. So we could subtract off some reference temperature, but those will just cancel out later. So we could subtract off a reference temperature. We could assume our reference temperature is just 0 Kelvin and not have to deal with it. So I'm taking a little bit of a shortcut here. Okay, how else is energy getting into our system?
Based on the nature, you also have flux coming into the pipe.
Okay, so we also have flux coming in. So I'm going to put that down here. Okay, what else do we need? Nimdo? Okay, so Nimdo is wondering why we don't multiply it by some type of area, and we do. I'm trying to help you guys get in this mode. So we're still doing this in terms of energy, which is going to be in terms of watts, and our flux will give us watts per unit area. So we need to multiply that by an area. What is the area that we need to multiply it by? The surface area of the pipe, okay. Can you guys give me some, I'm doing this because I graded your exams and want to emphasize this a little bit more. I want to help you think through what's the applicable area here. What is it? Oh, perimeter times delta x, great. So what's the perimeter? Pi r, yep. Let's actually keep it p delta x. That's what my notes are saying, so thanks, Blaine. Okay, how is energy getting out of our system? Okay, it's going down the pipe. So we have energy leaving our system because of the fluid flow, because of advection. So this MCT is energy flow by advection. So that's also going to be mCp times T, only now our temperature is going to be evaluated at x plus delta x. And in this particular case, there is something happening between x and delta x. Our fluid is having extra energy enter it, so we would expect that our temperature at x plus delta x is going to be slightly higher than our temperature at x because of that extra heating that's going on. So we would compile our energy balance. We are going to have accumulation is equal to m dot Cp times, and this, I forgot to specify that this is the mean temperature, trying to stay consistent with the book. To me, that's just the temperature of the fluid. So this is going to be our mean temperature evaluated at x minus our mean temperature evaluated at x plus delta x. And then we're going to have plus our surface flux times our perimeter times delta x. Okay? So what would be the next step? So yeah, we'd divide by delta x, and then we would take the limit as delta x approaches 0. So we would end up with an equation that looks like this. mCp times the derivative of our mean temperature with respect to x is equal to Qs times P. So we would just integrate that equation, and we would get our temperature profile as a function of x. So does anyone have a sense for what that curve is going to look like? If we plotted our mean temperature as a function of x, how do we expect that to look? Okay, so I want to point out constant flux. Our perimeter, is that a constant or a variable? That's a constant. How about our mass flow rate? Is that changing down the length of the pipe? Nope. It's going to be the same. How about our heat capacity? Will that change? So collectively, everything on the right-hand side is constant. So what's our line going to look like? So it's going to be, yep, just a straight line. So that solution is our mean temperature as a function of x is going to be equal to, and I'm skipping some steps here, but you can go back and do these yourself if you want to understand this better. So it's going to be our inlet temperature. This would have come from our boundary condition, plus Qs times P over m dot Cp times x. So everything here is just a constant, so this is just a line. So we would expect our, if we're applying constant flux down the whole length of the pipe, then our mean temperature, our fluid's going to enter the pipe at some initial temperature, some inlet temperature, and then it's just going to increase linearly. Okay, so that's how we get that equation. So that's actually going to be an important concept. As trivial and as simplistic as that may seem, that methodology, doing an energy balance, breaking your system up, can help you solve a wide range of problems. And we're going to be doing another flipped classroom kind of a thing with a problem like this the week after fall break. So if we have uniform surface heat flux, we are going to expect our mean temperature as a function of x to do something like this. What that would mean, if we're dealing with an entrance region, that may mean that our surface temperature is going to vary in this particular case. So providing, under this assumption that we have constant heat flux, it's still ultimately, heat is still getting into our fluid from the pipe into the fluid by convection. It's just that our boundary condition is this constant heat flux. So what would happen physically, especially for, well, what would happen physically is that our surface temperature is going to have to change so that in the fully developed region, this delta T is going to be constant the whole way. However, because in that entrance region, our H may be changing, you may actually see some nonlinear behavior for our surface temperature in that entrance region. This isn't particularly important. Okay, so now let's shift gears a little bit, and I want you to think through this problem. This one's just true or false, so you can just, well, think it through and then just take your best guess. So water is being heated as it flows down a pipe. It comes into the pipe at 20 degrees Celsius. It's electrically heated so that the inner pipe wall is maintained at a constant 70 degrees. So not constant flux anymore. Now we're trying to control, or we are controlling the pipe to this constant 70 degrees on the inner surface. Assuming a known constant convection heat transfer coefficient, the total rate of heat transfer from the pipe to the water can be expressed as our flow of heat is equal to H times PL. What is P times L? That would be just the total surface area of the pipe. So the total heat entering our fluid could be expressed just by Newton's law of cooling, where we're looking at our surface temperature, and here this TW would be our mean water temperature. So is that true or false? Can we just apply Newton's law of cooling just as we always have up to this point by Q is equal to HA delta T? So true or false? Should be pretty quick to answer. Just totally conceptual. Does anyone feel like they really know this answer and feel great about what they answered? Yeah, Alex? Okay, Alex says it's false. Why do you say it's false, Alex? Okay. Okay. Anyone else want to take a crack at it? Caleb? Okay, that may be the similar thing that you're saying. The temperature of the water shouldn't be a constant. Okay, so let's see how we did. All right, I'm surprised by this actually. So the correct answer is false. So it is false. So Alex and Caleb are both correct. And let's get in a little bit more to why. Why does this traditional form of Newton's law of cooling no longer apply in this particular case? Okay, so one thing is to remember is that, as Caleb pointed out, our water temperature is actually a function of x. So it's going to be changing. If we treated everything else in this particular problem setup would be constant. So that means that our Q, or our flux, I guess, would be a function of x. So our total Q, we're going to have to find in some different way. So while, as I said on a previous slide, Newton's law of cooling would still apply. So Newton's law of cooling still applies in this flux form. So at any particular instant, we could calculate the flux. However, over the whole length of the pipe, because our fluid temperature changes down the length of the pipe, we've got to reformulate how we calculate the total amount of heat going into our fluid. So that takes us to this next derivation. So a similar kind of setup, but now instead of constant flux, now we have a constant surface temperature, Ts. So how are we going to approach deriving this temperature profile? Okay. Titus is a couple steps ahead. It's going to be with an energy balance. So similarly, and this is just such an important concept to figure out, to know and understand how to do these energy balances. Okay, so if this is our x, here we have x, and then here we have x plus delta x. Okay, so again, let's stick with steady state. So we're going to have, and I'm going to skip through the accumulation steps. You guys can go back and do that on your own. So we'd have MCP, our mean temperature evaluated at x, subtract our mean temperature evaluated at x plus delta x. So now instead of that constant flux term, now we're going to have we're just going to put in the actual convection term. So we're going to have, this is H times Ts minus our mean temperature, and here is our perimeter and delta x. So this is our advection in term, here's our advection out term, and here's our convection in term. So we didn't skip too much. So we're doing this so heat is coming into our fluid, so the surface is hotter, so we're treating that as a positive term, assuming our surface temperature is hotter than our mean temperature at this particular point. So we treat that, we add that in. Okay, so for mathematical convenience, we're going to define our local temperature difference, and I'm going to specify that this is a function of x, is equal to our surface temperature minus our mean fluid temperature, which is also a function of x. So we're just going to stick with this as a definition, and we're going to work in delta t terms. That makes the math simpler. So we end up getting, we would divide through the whole thing by delta x, take the limit as delta x approaches 0, and we end up with a differential equation that looks like this. D delta t divided by dx is equal to, and with some algebraic maneuvering, we pick up this negative here, minus h times our perimeter times delta t over m dot times cp. Okay, so we would separate and integrate. So we're going to get d delta t divided by delta t is equal to minus h p dx divided by m dot cp. All right, what's the functional form that we're expecting our solution to be in? What's the integral of d delta t divided by delta t? So we're going to pick up an exponential. So first, the solution here is natural log. So we would get, if we integrated this guy, and I'm going to do a definite integral here, but you could still do it the boundary condition. I mean, still do this in general form and then apply boundary conditions. So our delta t at the pipe inlet, that's this delta ti, up to our delta t at a particular x is going to equal minus hp over m dot cp times the integral from 0 up to our x. So when we do that integration, we end up with the natural log of delta t at whatever x divided by our delta t at the pipe inlet is equal to minus h times p times x over m dot cp. Okay, so then solving this for delta tx, we get our delta t at any given x is equal to our delta t at the pipe inlet times e to the minus hp times x over m dot times cp. So now we can just solve for what our x is. So our mean temperature at x is equal to our surface temperature, so remember that surface temperature was embedded into our definition of delta X, minus Ts minus T mi multiplied by e to the minus h p x over m dot cp. Okay, so it's important to understand the math and the derivations and where these come from, because you may have other circumstances, and it's important to master this skill of doing a differential energy balance and integrating it to get an equation, because your boundary conditions may change, or your inlet conditions may change, or you may have something that changes dynamically. So it's important to be able to take a concept like this and turn it into an equation. However, it's also important to have some intuition of what this looks like. So let me just ask, does anybody feel like they could plot this equation based on just having an intuition of the system? How does this equation look? Or what does this temperature profile look like? So let's get rid of the actual equation and think about just the physics of the system. So here's X, here's our mean temperature. So if you remember, when our condition was constant surface heat flux, our equation was just a straight line. Our temperature just kept increasing linearly the further the fluid went down the pipe. So now we have our constant surface temperature. So if I plot our surface temperature, it just looks like that. Okay.